been a long way here, but this should tell you how bad Norwegian winter is if I need a bit of sun. So this is a joint work with Neil Barton that should be connected, hopefully, about new ways of axiomatizing the iterative conception of set, in particular the weak iterative conception of set. So this is the structure of the talk. First, I'll introduce you a bit something about the iterative conception, just to be sure that we are all on the same page. And then the two main sections will be about our new ways of conceiving about the axiomatization of the conception. And then in the end, I'll give you a bit of a general map of the project. So the iterative conception, it's probably the most popular conception of set that we have at the moment. In the words of Forster, it's the conception that tells you that sets are generated in layers by iterating generative process to old sets to create new ones. Then, if we want an instantiation of this, we just have to go read Gödel, when he says that the concept of set, according to which a set is something obtainable from the integers or some other well-defined objects by the rated application of the operation set off, it's something that has never led to any antinomy whatsoever. So this would be the reply to those that believe in comprehension, basically. And then in 51, Gödel specifies this by basically making the set of operation coincide with the power set operation. So the story becomes you generate sets in layers by iterating at every layer the power set operation, and then at limit layers you gather everything that you had before. And this is basically an intuitive story that tells you how the cumulative hierarchy of sets came to be. Now, recently I've done a bit of historical work identifying various ways in which the conception has been axiomatized to basically give you the axioms of set theory, so the classical ZL axioms. So what I call standard axiomatization divide into level and stage theories. So first level theories, basically you stay within a set theoretic language. And but what happens is that you move from the generative definition of the V alphas by transfinite recursion to a structural, or as Scott and Montague calls it, an explicit definition of the ranks of the set of what happens inside the V alphas, and you call these the levels. Or if you're someone like Boulos, you decide to add an additional primitive for the stages to your theory. And so you operate in a two-sorted language with variables for sets and variables for stages, and you quantify directly over the layers. Other options, so in standard axiomatizations, basically you keep only variables for sets, but you add a second primitive predicate along with epsilon. So basically these would be needed to render layer talk between sets. So you want to say that what it means for a set to be of a smaller level than another set. And for the proof theories here, this should be also interesting because another option advocated by Takeuchi is to axiomatize the ordinals as your stages. So you take the ordinal notions as primitives. So just to give you brief motivation behind the conception, there is a mathematical motivation and a philosophical motivation. The mathematical motivation is nicely put by this quote from an unpublished manuscript by Montague, Tarski, and Scott. So the thing is, basically, the standard model of set theory is a model where you have a V alpha or an R alpha in this case, where alpha is an inaccessible cardinal. Now, they propose to study instead systems for which that are satisfied by any R alpha whatsoever, where alpha is a non-zero ordinal. And they say, in this way, we obtain a short and simple set of axioms, which is adequate for the main purposes of these systems, and that should basically give you enough simple set theory. Then there is a conceptual or philosophical motivation, which is, again, provided us by Scott. And basically, here is saying, where does the axiom of, where does the set that we separate from in the axiom of separation come from? Well, if we ask Zermelo and other people like Skolem, Bernays, and Gödel, basically they will tell us that the answer to this question is just that. They are just the axioms. But as Scott says, this is a very simplistic view of the axiomatic process because it makes the axioms seem as if they had fallen from the sky and nothing is justifying them. Whereas what we want to do with the iterative conception is basically to find a way to justify the axiom, so to provide an answer to the question, where do the axiom come from? So as Scott says at the end of the quote here, this is a simplistic view of the axiomatic process, but it is a very widely held view and one that it's easy to fall into when considering only the formal axioms without their intuitive justification. Let us try to see whether there is another path of the same theory, more obviously based on this underlying intuition. Turns out the path that there is a path, and so I'll present you briefly two ways of axiomatizing this iterative conception. The first one is championed by Tim Button in recent work on level theories. So you start by defining this notion of a potentiation, which is basically the supertransitive closure of a set, and then you define two twin notions, that of a history and that of a level. So basically the idea, you should imagine the levels as the V alphas and histories as accumulations of the V alphas, basically, and then you close everything under this operation. So this is just like, let's say, a mock-up version of power set. And then level theory is this very simple and brief theory. So you have the axiom of extensionalities, separation in second order because we also want a categoricity result. And then the most important axiom is this certification principle, which tells you that every set lives at a level, which is basically an analog of the foundation axiom formulated in terms of the V alpha. So when you would say for every axiom there is an ordinal such that for every set there is an ordinal such that that set lives at the V alpha indexed by that ordinal. So this theory is pretty simple, but also not so powerful by itself. It can give you only separation, union, and foundation. Proof of foundation is especially critical in this theory. But if you add some bolt-ons, especially if you add a principle telling you that there is an infinite level, and a principle stating that that no set can be mapped unboundedly into all the levels, then you notice that this is equivalent to the axiom of infinity, this one is equivalent to the axiom of replacement, and so your level theory becomes equivalent with Zn. So this is one way of axiomatizing the iterative conception according to the standard story. The second way is if you add these bold-faced variables for stages, and then you read that square subset as the set is formed at a stage, and the other as a set is formed before a stage, you can have stage theories formulated in this way. So one again is Button. You have the axiom of extensionality. No escape from it. Boulos said that it's somewhat an analytic principle of set theory. Then you have an axiom of order telling you that the order between the stages is transitive. A principle of priority, which tells you that all the elements of a set are formed before the set itself is formed at some stage. Staging again, which says that every set is formed at a stage, and then a specification principle, which is basically an analog of separation, which tells you if you have all the satisfiers of some property before a stage, at the stage immediately afterwards, you find the set of all those things. So this is one way of doing stage theories. Another way is based on Scott. So in this case, you have again extensionality and staging, which equals restriction. But then instead of specification, you just plug in separation, so normal theoretic separation. And then you have this accumulation axiom, which basically is telling you what are the conditions to be satisfied for a set to live at stage. It's basically saying that stages accumulate everything that there is before them. So this was the standard plain iterative conception people are used to, but these fall under what my co-author Neil Button calls the strong iterative conception. So the whole output of the degenerative process, which is power set in this case, is found immediately after the stage at which the process applies. Here we're interested in something different, which is called the weak conception. So each output of the process is found at some later stage than the one at which the process first applies, but we are not committed to saying whether the stage is the one immediately after you first apply the process. So we have something that we call the weak power set based iterative conception. So you generate sets in layers again, but at each layer you gather some of the subsets of the sets found in previous layers, and there are no other sets outside this layer. Now, how can we make this sum more precise? Well, we can appeal to a notion that set theories are accustomed to, which is that of a definable or better, a constructible set. So basically, the first axiomatization of the weak iterative conception is an axiomatization of Gödel's constructible universe. So you generate in layers the constructible sets. So just to remind you of how the constructible universe look like. So instead of iterating full power set, basically Gödel provided us this notion of a definable subset. So that D plus over there. So D plus is the set of all subsets of A, definable over that structure with parameters in A. So you can use this notion to define this hierarchy here. So you start from the empty set, and then you iterate a definable power set, and they make union at limit stages, and you basically obtain an inner model of set theory. Now, our aim here is to mimic what Button did with his level theory. So if level theory is the theory satisfied by any non-zero V alpha, we want something that we call constructible level theory to be a theory satisfied by any non-zero L alpha. But we immediately run into a problem because a question is, how can we describe L in a purely stage or level theoretic sense? Because of course, when you say a set is definable over some structure, there is some sort of meta-theoretic talk going on, which is not easy to capture in this context. So formulating definability over a structure, stage or level theoretically, seems weird without doing it parasitic on a strong background set theory. But fortunately, Gödel provided us the solution, which are the Gödel operations. So this is basically another way of obtaining the constructible universe that Gödel formulates in the article on the continuum hypothesis. So instead of iterating definable power set, he formulates 8, but he has 10 operations, which you basically then close on to obtain the same thing that you obtain by iterating definable power set, so namely the constructible universe. So these are basically operations that tell you, if you give me some sets, then I will give you all the sets definable from them. So you get the pair, you get the graph of the membership relation, Cartesian product, intersection, complement, and so on. So basically, our strategy was to use this to define what definable subset means. So power set with delta, which basically is the result of applying the Gödel operations to all the members of X, then it's also in Y. So this should be very long disjunctions of saying that A is either the result of G1, G2, G5, etc., etc., etc. So in this way, we basically hooked up a way to close under definability, and then we basically reproduce Button's theory, the same theory, but by using the definable subset instead of the standard subset. And so then constructible level theory is literally almost the same theory, but where the level is a definable level. So these levels, in this case, should correspond to the L alpha instead of the V alpha. So we have as an immediate result, analogous to Button, that constructible level theory proves separation, union foundation, and also the axiom V equals L. So the axiom stating that the universe actually corresponds to the constructible universe. So again, just like in Button's case, we can add some bolt-ons to obtain the rest of the depth. So I call the theory CL2 plus, which is the constructible level theory, augmented with some bolt-ons, so endless tells you that there is no last level. Infinity tells you that there is an infinite level. Unbounded tells you that, again, no level can be mapped unboundedly into the hierarchy of the levels. It's a mock-up of replacement. And then we have also this principle that in the original level theory you do not need, because in the original level theory you know that all the levels gather all the subsets. In this theory you don't know this because these are constructible sets. So the hierarchy grows much slower than V. So we need to ensure that for every set there exists a level containing all the subsets of that set to have power set. So again, after team's work, CLT plus is equivalent to ZF plus the axiom of constructibility, so D equal L. Now, there is a problem, and this is the reason why I highlighted separation in the previous slide. So remember I told you that we want this theory to be satisfied by any non-zero L alpha. Now, full separation, even let alone the second order version that we have, is not satisfied in any L alpha precisely because L grows much slower than V, so you don't have all the subsets at every level. And there is this conflict between the fact that the proof of foundation is quite crucial in this setting to have a well ordering of the levels, but to prove foundation we need either pi1 separation, if we go after these two proofs by Potter and Button, or sigma 2 separation if we use Scott proof. And this conflict with the fact that separation is not satisfied in any L alpha. So me and Neil then ask ourselves, so what are the models then that satisfy constructible level theory if they're not all the L alpha? Well, thank God we had Joel Emkins at a conference in Singapore that answered the question for us, at least partly. So the models of CLT will be DL alpha that satisfies separation, namely alpha is a bad fixed point. Why? Well, because if alpha is a bad fixed point, then DL alpha is equivalent to the corresponding D alpha. So you have full power set over there. Alpha is a cardinal, again, because L grows lower and catches up on all the subsets at limit points. Or, and this is quite interesting, if you have an L alpha that is comprised or chained between two L kappa for kappa regular limit cardinal, and this is because of Gödel condensation lemma. So basically the condensation lemma tells you that if you have an L structure and an elementary substructure, if you take the Mostowski collapse of that elementary substructure, so the transitive structure generated by that, then that is a L alpha. And since elementary substructure preserves satisfaction, then we are sure that also in this L alpha we have separation. So we take this to be an interesting lesson on the predicative nature of L, which was described first by Pfefferman in a 2005 paper. So if you want the constructible level theory to be an explicit description of the L hierarchy that models full ZF, then you must give up on the general character of level theories because you would not have a theory satisfied by any L alpha, which is non-zero. Or if you want a constructible level theory that has the same general, maximally general character of level theory with respect to V, then we probably end up with some more predicative theory, namely Kripke-Platek set theory, which is the next step in the construction of level theory. So basically, we define two new theories, which are constructible level theory sigma naught and constructible level theory delta naught, which is basically just a constructible level theory, but where we take out separation and instead we plug in either sigma 1 separation or delta naught separation. Then again, since Kripke-Platek is a theory which does not have full replacement, but instead has delta naught collection, we thought of adding to the theory delta naught reflection. So basically, this is the classical reflection principle that you have in set theory. So if there is something which is true of all the hierarchy, you can reflect it down to an initial segment. The only restriction that we are imposing now is that the formula must be delta zero to satisfy Kripke-Platek. So then our conjectures are, the first one is based on a proof by Jensen, which is not published, but it's in the folklore. So all the L alpha satisfying sigma 1 separation are the same L alpha satisfying critically-platex set theory. So basically what happens then is that CLP sigma naught is satisfied by all the L alpha that have alpha as an admissible ordinal. So basically the theory proposed by Bearwise in 75. Then you have what we wanted, that if you have CLP delta naught, then that's the theory actually satisfied by any non-zero L alpha. And then if you plug in reflection, you obtain full critically-platex set theory. We are still working out how to get foundation actually, because this may be an issue given that we have weakened separation. And then if you have infinity, you obtain critically-platex set theory sub omega, so with infinity as well. So this was a first approximation of how level theory for a weak iterative conception should look like. Now, a thing is that in this case, the stages are still well ordered by membership. And one may also object that if we take D plus as a primitive instead of power set, then this is still an instance of a strong conception, because at every stage you obtain the full definable power set of every set. So one may still say, well, actually you want to proceed by iterating definable power set, but in a much weaker way. So like you take, you realize each formula for each set of parameters separately in this iteration, and then you would obtain something even weaker. So a question would be, is this true? Are there versions on which the stages are not well ordered, but still well founded? And the answer turns out to be yes. We hypothesize that there will be many such, but here we consider three, namely level theories for a version of the iterative conception of set that should sanction countabilism. So the thesis that every set is countable. So, I mean, it's not super bonkers to say that Cantor's theorem may not hold, because maybe we don't like power set. So the first one, the bare bones countability story, says that sets are from these stages and you iterate enumeration. So at an additional stage, you find an enumeration of every set that you had at previous stages. And there are no other sets outside those that will be built in this way. So pretty straightforward. We can refine this a bit by having the forcing countability story. So you, again, form setting stages, but this time at every stage, you find for any partial order and family of dense sets at the previous stage a forcing generic. So basically you iterate the collapse forcing and anything definable over the previous stage. Again, there are no other sets outside those built in this way. Third, the arbitrarial countability story. At additional stage, this time you find an enumeration for sets at previous stages, definable sets in terms of those enumeration, and also the transitive closure of any set. So these are three ways of refining the idea of countabilism. So question, how shall we get an enumeration? Well, Tim Button has done much of the work for us. So basically in a 2024 paper, he has a theory which is synonymous with level theory, but this time it's based on characteristic functions rather than epsilon and membership. And our plan is basically to build a countability level theory by adapting the template of functional level theory and now taking an enumeration function as primitive. So it's not quite the same as a characteristic function, but it's somehow similar. So we are plugging in this primitive enumeration. So a metaphor to explain what's going on here is basically you should imagine a toddler that learns how to count, and he learns how to count along the ordinals. Then when he reaches limits ordinals, he learns new way to count and combine this enumeration. So in this way, you generate basically a branching structure, because first of all, he counts up to omega, but then he adds enumeration based on omega, so he can go this way or this way and have whole sorts of structures. So our expectation for this theory is that the bare bone story basically is a story that tells you that if you ever get an infinite set, you add countably many reals. So levels are just countable sequences of real numbers. The forcing story basically tells you that levels are just the countable alpha over some G, so that's the relative constructibility operation for a G generic over L alpha. And finally, the arbitrary story is just a story that tells you that levels are the countable L alpha for R and real number. And so this is still very much work in progress. We have still to figure out how to build a nice axiomatization of this, but more or less this is what we are expecting to obtain from this theory. So to give you a map of how the landscape of the iterative conception is, so here you have a bunch of generative processes, the most popular studied so far, and then we divide it in strong and weak conception. So if you iterate power set, you get level theory. If you iterate power set but conceive the von Neumann, so by having characteristic functions, you obtain functional level theory. This is also interesting. BLT is Boolean level theory. So you basically iterate power set from below, but then from above, you iterate absolute complement. So you start from the empty set and the universal set, and then you iterate power set in this direction, and then in this direction, you take out everything that you generated before. So you basically generate an algebra. PLT, plural level theory, is the theory I'm working on. Here you iterate abstraction from pluralities to sets. This is the functional based on enumeration, so the countability level theory. Notice that the strong version in this case is immediately inconsistent, because if you have that every set is countable plus at every level you get all the enumeration, you get immediately inconsistency. And then delta plus is the theory I've talked before, so based on taking definable subset as a primitive operation. And then in the weak case, you have the theory about. So constructibilist level theory, the same version done with characteristic function. Here we have no idea what is going on. Critical prologic, the logic championed by Oyster-Linnebo, our countabilist level theory, and then the constructibilist level theory in a still weakened sense. So for what concerns the set theory that this theory give you, so all the strong one basically point towards ZF. The strong contabilist conception is straight away inconsistent because of the Scott-Cohen paradox that has been formulated by Neil and also in a joint work between Neil and Cy Friedman. The weak conception, instead, it's a bit more interesting because, so critical plural logic, so this weird logic of plurals points towards the def minus power set plus every set is countable, or if you add in enough juice, you get you end up with full ZFC. The constructible level theory we just saw, so we have ZF plus V equal L, or Quidquidbatek plus V equals L. And finally, our conjectures for the countabilist level theory is that the bare bone story is super weak. It actually tells you only that every set is countable. We don't even know about union, foundation, pairing, extensionality. We don't know anything basically. The first story points towards ZFC minus power set plus every set is countable plus every set is generic over some and alpha. And finally, the arbitrary story points toward these nice theories that F minus power set plus every set is countable. So yeah, I think this was all. Thank you very much.